In this video, we were going to take a look at the graphics pipeline and create a box shader using Godot shading language. Let's first understand how things are actually rendered on screen. This happens through a series of stages known as the graphics pipeline. First, the pipeline takes in vertex data, but before we talk about vertex data, let's understand what a vertex actually is. A vertex is simply a single point in 2D or 3D space. It's the building block of all shapes. So, vertex data is all the information attached to each vertex. The must-have piece of data is position. Then there are optional but very common attributes. First, we have color. Next, we have UV. These are coordinates that tell the shader how to map a texture onto a surface. For example, to add a texture to a cube, we need to unwrap it. That means flattening the cube into its 6 2D faces. The entire unwrap fits inside the single square called UV space 0, 0 at the bottom left and 1, 1 at the top right. This unwrapping allows the cube to move, scale or rotate while the texture still looks correct and doesn't stretch or distort. Next we have normals. It's used in lighting calculations. The graphics pipeline begins with the input assembler, the stage that organizes vertex data into primitives like points, lines, triangles. The next stage is the vertex shader. It determines each vertex position, rotation and scale. Tessellation and geometry shader are optional stages. They are often skipped in 2D games or simple 3D games. Tessellation subdivides primitives into smaller triangles, producing smoother or more detailed surfaces. The geometry shader can modify, add or remove primitives. For example, in particle systems, a single vertex is expanded into a quad. Since a single vertex isn't visible, this approach is more efficient than sending quads to the graphics pipeline. The next stage is rasterization. This stage converts primitives into fragments, which are potential pixels on the screen. They were called potential because some may be removed. Clipping discards fragments outside the camera's view, and culling discards fragments from faces that aren't visible. The next stage is the fragment shader, also called the pixel shader. This stage runs for every fragment generated by the rasterizer and determines its final color. The final stage of the graphics pipeline is the pixel operations stage, also called the output merger. This stage works with the frame buffer, which is a memory buffer that stores the current color, depth and stencil values for each pixel on the screen. Each fragment from the fragment shader goes through the following operations using the values already stored in the frame buffer for each pixel at the same position. The stencil text acts like a mask. It compares each fragment's stencil value, which is an 8-bit number, with the stencil value already stored in the frame buffer pixels using a condition that we specify. If the fragment passes the test, it is drawn, otherwise it is skipped. A common use of the stencil test is for creating outlines. First, we draw the object normally and assign its pixels a stencil value, for example 0x00. Then we duplicate the object, slightly scale it up and assign it a different stencil value like 0xff. Finally, we set the stencil test on the duplicated object to only draw fragments where the stencil value is not equal to 0x00. The depth test checks whether fragment is closer to the camera than the existing pixel. Each pixel has a depth value, where 0.0 represents the closest possible distance and 1.0 the farthest. If the fragment is not closer, it is discarded. After stencil test and depth test, we have blending. Blending combines the fragment's color with the existing color in the frame buffer. If the fragment's alpha is 1, it fully replaces the existing pixel color. If the alpha is 0.5, the final color becomes a mix of the fragment and the existing pixel. Vertex, fragment, tessellation and geometry shaders are all stages where you can write code to modify how objects are rendered. However, in most cases, you will primarily write vertex and fragment shader code, since they handle the transformations and pixel coloring. Now that we understand how the graphics pipeline works, Let's dive into writing our box shader in Godot. Here's a quick overview of the project. The game window is set to 1280 times 720 and we have two scenes, a player scene and a main scene. The main scene includes the background sprite and instantiates the player. Now let's create the box shader. In the main scene, create a color rect node and set its size to 1280 by 720 to match the window. Next, add the shader material to the color rect. Create a new shader for that material. Then click on the shader to open the shader editor. So what's happening in this shader? First, we declare shader type canvas item. Next, we have two uniforms. Uniforms are exposed in the inspector under shader parameters. So we don't have to open the shader code every time we want to tweak values. The first uniform is noise texture. So let's assign a noise texture in the inspector. The second uniform is fog opacity, which we have set to a default value of 0.3. Fragment shade, we know it transforms every single pixel and determines that pixel's final color. Inside it, we have this. The texture function is built into the shader language. It samples our noise texture using the current UV coordinates. In simple terms, it gives us a vector value containing red, green, blue and alpha for each pixel. Since our noise texture is grayscale, all three color channels are the same, so whether you use .r, .g or .b, you will get the exact same result. Then we have color.a equal noise times fog opacity. This line controls the transparency of the fog. Color.a is the alpha channel of the color. It determines how visible or transparent each pixel is. The noise value comes from sampling the noise texture, giving us variation for the fog. The fog opacity uniform lets us control the overall strength of the fog. Now let's start moving the fog. Add repeat enable to noise texture. Then we add a new uniform called speed. Inside the fragment shader, add this line. Remember, time is a built-in uniform, so its value is the same for all pixels during a single draw call. However, with each frame, time increases. In a 60 FPS game, time increments by roughly 0.0167 per frame, so the UV values shift slightly every frame. For example, 0,0 UV becomes minus 0.0167, minus 0.0167. This is why repeat must be enabled on the noise texture. It allows the texture to wrap around as UVs move beyond 0 and 1. But enabling repeat alone isn't enough. The texture also needs to be seamless, otherwise you will see visible jumps or edges when it wraps. By multiplying by speed equals 0.01, we can slow down the movement. And we can adjust this value to make the pop faster or slower depending on the desired effect. Finally, we replace the built-in UV with our UV variable. Next, let's make the area around our player clear of fog. First, we add the following uniforms: player position, circle radius, canvas size. Inside the fragment shader, we have this line: vec2 pixel box equal UV times canvas size. This multiplies the normalized UV values by the canvas size. So for example, UV equals 0.5, 0.5 becomes 640, 360. Next, we calculate the distance from each pixel to the player. For example, if the player is at 0, 0, the pixel at 640, 360 will have a distance of the square root of 640 squared plus 360 squared. Then we create a smooth circular mask using smooth step. Smooth step is a built-in function that outputs values between 0 and 1. In this case, pixels closer than circle radius minus 200 get a value of 0. So when we multiply it with the alpha value, alpha becomes 0 and the area is fully cleared. Pixels between circle radius minus 200 and circle radius gradually fade from 0 to 1. Pixels beyond circle radius get 1. Finally, we apply this mask to the alpha. I said finally, but one more thing is left to do. Passing the player's position to the shader. In the main scene, create a script and add the process function. Inside it, add this line. This line represents the work color rect and sets its shader parameter player position to the player's global position. This allows the shader to know where the player is and clear the area around them accordingly. So this is the final code, and you can tweak it however you like. If you made it to the end of the video, consider subscribing and giving it a thumbs up.